In this videocast, we'll take a look at solutions called buffers. Buffers are solutions that resist change in pH. And the reason that they resist a change in pH is because they contain both acidic and basic substances. You must become a good recognizer of substances that contain both acidic things and basic things. Here are a few examples, or here is the general trend. If something contains a weak acid, generally symbolized by the symbols HX, where H is the acidic part of the acid and X is the anion, and a solution also contains the anion of the acid, which, if you notice carefully, is the conjugate base, what's left over after the acid has released its proton. Now we have a conjugate base and an acid in a solution, and they have X in common, similar to the common ion effect, except one must be a weak acid and the other has to be the anion of the acid. The other way you can have a buffer is if you have a weak base. Weak base, remember, is something that is able to accept protons. For example, NH3, a weak base. Once the base has accepted its proton, it'll usually form a positively charged thing, like NH4, which, if you notice, is the conjugate acid of this weak base. If both of these are in solution together, we now have a basic thing and an acidic thing. And they have a common ion because this is the conjugate acid of the weak base. Here are a few examples of where a weak acid and a weak base, a weak acid and its conjugate, or a weak base and its conjugate exists together. For example, let's say we had NH3. Inside the NH3 aqueous solution, which is a weak base, we dissolve some salt. The salt is NH4Cl. NH4Cl is super soluble in water, and so it will give us NH4 plus ions and Cl minus ions. This weak base and this conjugate acid right here form a buffer solution. Why is it important to have both a base and an acid in the solution? Well, remember, buffers are things that resist change in pH. And if you would add a strong base like KOH to the solution, the OH minus right here would react with the acid. If you would add a strong acid to the solution or an acidic substance to the solution, the H plus would react with the base. That's how a buffer buffs, or takes care of, a change in pH when something is added to it. Here's another example. Let's say, for instance, we had the weak acid HF, and let's say we added to it the salt sodium fluoride. Sodium fluoride, of course, is very soluble and give us some Na+, and if you notice, the conjugate base of this weak acid. We now have an acid conjugate base pair. These pairs, weak acid and its conjugate base, or weak base and its conjugate acid, will form buffer solutions. A buffer is a solution containing a weak acid base and its conjugate base acid. It must be a combination of a weak, notice it has to be a weak acid or base, and the conjugate of that acid or base in the form of a base or an acid. Why does it have to be a weak acid or base? Well, if we put a strong in there, remember the strong will completely dissociate, and so we won't have any more of that strong base or acid there anymore. We'll just have its ions. Let's take a look at the first sample problem, and if you don't have this sheet in front of you yet, please find the sample problems for Chapter 17 and take those out. The first question from section 17.2 says, which conjugate acid-base pairs will function as buffer solutions? Which conjugate acid-base pairs will function as buffer solutions? Remember, the definition of a buffer is that we have an acid, like HA, and its conjugate base, A minus, both present in the solution. Or we have a weak base and its conjugate acid. Let's take a look at this first solution. This is HCHO2. Well, this is an acid, and is it a strong or weak acid? Well, we didn't memorize it as one of our strongs, so it must be a weak acid. And then we have some CHO2 minus. You can just barely see it, but there's a little minus sign right here. And if you take this acid and react it with water, you'd get some H plus and some CHO2 minus. Oh, that means this stuff right here would be in common with the weak acid, and so we would have the acid and its conjugate base both present in the solution. Therefore, yes, this first one would be a buffer solution. Let's take a look at the second one now. This one's got HCO3 minus and then CO3 minus. Well, HCO3 minus could be a proton acceptor and then become H2CO3, or it could donate this proton as well and become CO3 minus. Aha! CO3 minus would be what it would form if it was acting as an acid. It would form some CO3 minus right here, and also some H3O plus. Notice this right here, CO3 minus, is the conjugate base of this acting as a weak acid. And remember, to be a buffer solution, you have to be a weak acid and its conjugate base pair. And so this too, yes, would be a buffer solution. What about this last one, HNO3 and NO3 minus? Well, I've got an acid here, HNO3, and I've got its conjugate base. What's left over after the acid has released its proton? Would that be a buffer solution? Well, you'd think it normally would be, but remember, the one characteristic that a buffer has to have is it must have a weak acid or base and its conjugate base or acid. Notice it has to be a weak acid or base. And what is HNO3? Well, HNO3 is a strong acid. A strong acid. And so no, this one cannot be a buffered solution. Because if HNO3 reacted with water or dissociated in water, it would have one giant arrow going to the right, and it would form H3O plus and NO3 minus, which is a good thing, but there would be none of this left, and we would only have the conjugate base in the solution, no HNO3 acid, the actual acid in the solution. So, two of them can be buffers, one of them can't. Let's take a look at some calculations we can do with buffer solutions. On the next page, the first problem says, what is the pH of a buffer that is 0.12 molar in lactic acid and in its conjugate base, lactate ion? And it gives us the Ka of the lactic acid as 1.4 times 10 to the negative 4. Well, the first step in this type of problem is the same as we did with common ions, and that's to recognize what is your weak acid or base. In this case, it tells us that it's a buffer, so look for the weak acid or the weak base and write an ICE table for that type of thing. So here's my equation for lactic acid acting as a weak acid. HC3H5O3 plus water, and it's going to form some H3O plus and some C3H5O3 minus. Now, write an ICE table for it. When you write the ICE table, put ICE down the side and put in your concentrations that you have. It tells us that it's 0.12 molar in the acid, and it's also 0.12 molar in lactate ion, so 0.12 molar to start with. Remember, we don't care about the water, and the H3O plus doesn't exist yet because we haven't dissociated this. Now, when a change takes place, I'll lose X, and I'll gain X, and I'll gain X, and at equilibrium I'll end up with 0.12 minus X, X amount of the H3O plus, and 0.12 plus X. Now, if I want to find the pH of this, of course I'm going to focus on finding X. And I can set this up equal to my Ka, where Ka is equal to products divided by the reactants, If I slide this up a little bit, you might be able to see a little better. And I can make some assumptions. I'm going to assume that this x is small compared to 0.12, and I'll assume that this x is small compared to 1.2. And lo and behold, look at that. If the acid and its conjugate base are equal in concentrations, they in effect cancel each other out, and my H plus ion concentration is equal to the Ka. Pretty cool. If I want to find the pH of it then, I'll simply take the negative logarithm of 1.4 times 10 to the negative fourth. And if I can do that in my head, I'll be doing the negative log of approximately 1.4 plus the negative log of 10 to the negative fourth. This, of course, is going to end up being about 4. And this right here, the negative log of 1.4, and the negative log of 3 is 0.5, so I'm going to guess that this is going to be approximately 0.2. So I'll subtract 0.2 from it, and it'll end up being about 3.8. If you want to do it in your calculator, you should come up with a pH pretty close to 3.8. Well, in general, we can take a problem like this because it's really valuable to be able to calculate the pH of a buffer solution quite quickly. And we can say for a solution with a weak acid and its anion in it, I'll zoom in on this so you can see it just a little bit better. We can say that the Ka expression is going to be H3O plus, the product, and its anion, plus X, divided by the concentration of the weak acid minus X. And if you forgot, we just did this up here, where we had the concentration of the H3O plus as X right here, and we had the anion right here, 0.12 molar plus X, this guy right here. And then on the bottom we had the acid losing X right here on the bottom. So if you look back at the in general one, we can say that it's H plus times the anion plus X divided by the acid minus X. We'll ignore these X's and we'll say that they're small compared to X minus and HX. And if we solve this thing for H3O plus, remember we want to easily be able to find the pH, and if we know the H3O plus, hey, we're just a negative log away from finding the pH. We can find that H3O plus is equal to Ka times HX. That's bringing that to this side and bringing this over here to this side underneath, divided by X minus. And if I want to find the pH directly, why not take the negative log of both sides of this equation? If I do that, now I have the negative log of H3O plus, and I have the negative log of this side of the equation. Well, I'll rewrite that. The negative log of H3O plus, of course, is the pH, and that's equal to the negative log of Ka. And since this is a multiply sign right here, I could actually put it as plus the negative log of the acid concentration divided by the base concentration. Well, where are we going with this? Well, this is the pH. The negative log of the Ka can also be called the pKa. And then I've got minus the log of the concentration of acid over the concentration of base. I can use this equation to quickly and easily find the pH of any buffer solution as long as I know the pKa of the solution, the concentration of the acid, and the concentration of the base. Now, the equation sheet on your AP exam actually takes this equation one step further. We were at the pH is equal to the pKa minus the log of the acid divided by the base. But remember, when you have the acid divided by the base, you can split it up and write it as the log of A minus the log of B. A meaning acid, B meaning base. Now if I distribute this negative in here and then recombine it, I can actually get the equation pH is equal to pKa plus the log of base over acid. Notice there's a plus sign in here now because I went and distributed this negative through there, and then I took the negative thing and put it on the bottom, and the positive thing and I put it on the top. This is the way the equation is given on the AP exam sheet, and you'll see this equation in your textbook on page 727. This equation is called the Henry-Hasselbeck equation. You can also solve a Henry-Hasselbeck equation for buffers to find directly the pOH. The same can be done to solve for pOH. In this case, the pOH turns out to equal the pKb plus the log of the acid over the base. This is the shorthand writing for the acid, the conjugate acid of a base, because remember the base will gain a proton and it will get a positive charge. Both of these equations are given on AP exam sheet, and you will not be required to derive them like I just did. You simply can now use and abuse both of these equations. They're both called the Henry-Hasselbeck equation. This is the most popular one right up here because it solves for pH directly, and you can always solve for pOH later. Let's take a look at an equation now, or a problem now, that will use this type of equation. Look at the second problem on this page. This one says, how many moles of NH4Cl must be added to 2 liters of a 0.1 molar NH3 solution to form a buffer whose pH is 9. Assume that the addition of NH4Cl solid does not change the volume of the solution. Well, it tells us that it is a buffered solution, and we know that we want to find something about it since we know the pH. So we may as well look for using the Henry-Hasselbeck equation, because from that we can find out concentrations of the acid or the base. The Henry-Hasselbeck equation says that the pH of a solution, which in this case is equal to 9, is equal to the pKa plus the log of the base concentration over the acid concentration. Well, which one's the acid and which one's the base in this solution? We have 0.1 molar NH3. Hey, that's a base. I've heard of that before. And we'll also have NH4Cl. NH4Cl, remember, dissociates to form NH4 plus and Cl minus. The NH4 plus is the conjugate acid of this NH3. The NH3 is the base, so we'll put that on the top. And then down here, we're looking for the concentration of the acid. If we find the concentration of the acid, well, we know the volume of the solution, and if you remember, molarity is equal to moles divided by liters. If I know the concentration from right here, and if I know the volume of the solution, 2 liters, I can take molarity times volume and I can find the moles of NH4Cl that should be added. Okay, let's work the rest of the problem now when we know kind of how to set it up. 9 is the pH. It's equal to the pKa, and the pKa we'll have to calculate. That's the negative log, remember, of the Ka of NH4 plus. And if we look up the Ka of NH4 plus, we'll put that in there. Plus the log of 0.1, I'm going to put this in parentheses, minus the log of the thing that I'm looking for. I'll put that as A in brackets right here. 9 is equal to the negative logarithm of the NH4 plus's Ka, which turns out to be 9.25. Plus the log of 0.1, and the log of 0.1, you might be able to do that in your head because it's actually the log of 10 to the negative 1, plus a negative log of A. Right here, that's what we're going to look for. This one, the log of 10 to the negative 1, of course, is just going to be negative 1. So we end up with 9.25 plus a negative 1 plus the log, negative, don't lose that, of concentration of A is equal to 9. I combine these two, 9.25 plus negative 1 turns out to be 8.25. 9 is equal to 8.25 plus a negative log of the concentration of A. I'll subtract 8.25 to both sides of the equation, a negative 8.25, so I'll lose 8.25 on this side, lose it on this side, and I end up with 0.75 equal to the negative log of A. Now, solving just for the log of A, I think I'll multiply both sides by a negative. So then the log of A is equal to 0.75. Now, to get A by itself, I don't divide both sides by a log. Be careful of that. I have to use the 10 to the x key, and I'll put in 10 to the negative 0.75. And to approximate that, remember, 10 to the negative 0.7 is about 0.2, so it's a little bit smaller than that. So I'm going to guesstimate it as about 0.18. This is my concentration then of my NH4Cl in the solution. Remember though, the question didn't ask for the concentration, it asked for the moles in there. And if you remember, to find the moles, I'll take my molarity times my liters, and it said that it is a 2-liter solution. So I'll take my molarity, 0.18, times my liters, 2 liters, 0.18 times 2 is 0.36 moles dissolved in the solution. So that's using the Henry Hasselbeck equation to solve for a concentration that's unknown in the in a buffer substance. The last question on this page says, what is the optimal pH buffered by a solution containing acetic acid and sodium acetate? And it tells us the Ka for acetic acid is 1.8 times 10 to the negative 5th. So what the heck does the word optimal mean? What is an optimal buffered solution? Well, remember what buffers are. A buffer wants to resist the change in pH. And if you look at the Henry Hasselbeck equation once again, it wants to have a lot of base and it wants to have a lot of acid in it, because then it can react with either an acid or a base that's added to it. It wants lots of both of these to be optimal. And what's ideal, of course, is if we have the same amount of base as we have of acid, and we have a large amount of both of those, so it can resist the change in pH quite a bit. So why does it want this? Because if I add H plus to the solution, what will the H plus do? Remember, H plus shows you there's an acid. Well, it will react with the base right here, C2H3O2 minus, which is in the buffered solution. Well, let's say I add OH minus, add a base to the solution. What will it do? Well, it will react with the acid, the HC2H3O2. So I want equal amounts of both of those in the solution. So it wants to have a lot of both of those to resist a pH. So let's just choose an amount and make it equal. If I put this into the Henry Hasselbeck equation, the pH would then be equal to the negative log of the Ka, because that's my pKa, plus the log of, I'm just going to choose something, 1 molar and 1 molar in both the base and the acid, because then I'll have a lot of both. Well, this is really convenient, because 1 divided by 1 is 1, and what's the log of 1? Well, the log of 1 is 0, right? So this whole thing then goes away. And what is my optimal pH? Well, it's just the negative log of the Ka. Therefore, the pH, optimal pH, if you take the negative log of this, is about 4.7. Good luck with your buffer problems.